Question 14 in homework number 7, which is due on Monday. And in it, there is a circuit diagram. And it's supposed to, the question is this a 2 by 2 multiplier? 2 bits in, 4 bits out. And I guess sort of another way to put it is, what does this do? What does it do? How do we analyze this? Any ideas? Well, what would you get here, for example? Yep, that's good. And then, what do you suppose this would be over here? So the input here, that's a... There you go. A0, B0. And then, what do you suppose you'd get over here? I think that's an A1. And this looks like B0. So A1, B0. And then what do we get over here? Any ideas? Got A1 over here. A1, B1. Looks good. So then, what do you have over here? Looks like A0, B1 is going in, and that's A1, B0. So it looks like A0, A1, A0, B1, B0. Does that look about right to you? So far, so good? Anybody got any questions about what I've done so far? Right, I got B0, A0, B1, and then I got over here, I got A1, B0, and I just wrote out A1, A0, B1, B0. So that seems okay. So then what's C3? Well, it's going to be that times this, but A1, B1 is already in there, so that doesn't add anything. So C3 must be equal to A1, A0, B1, B0. So we're already starting to get some output. Let's see now. What do you suppose C0 will be? Well, I guess we know that already. It's going to be A0, B0. And then what do you suppose C1 is going to be? Well, that's more challenging, right? Because why? Because it's exclusive OR. But that's all right. I mean, we could write it over here if you like. C1 is equal to, and it looks like the input A0, B1 exclusive OR with A1, B0. And then C2, it looks like it's going to be right here. A1, A0, B1, B0, exclusive OR with A1, B1. What do you think of that? Does that look all right to you? So, What can we do about that? Does it look like we have enough to be able to create the truth table? Or do we need to simplify some more? I'd like to simplify. A exclusive OR B is equal to AB or AB prime prime. So if that's true, and this is A, then that's B prime. Oh, that's multiply. And then OR, and this is A prime. And then this is B. We can simplify this by using De Morgan's theorem and then cross multiplying. And then we have to use the distribution theorem. A1 times A1 prime is 0, but the other terms are going to be non-zero, except for B1 prime times B1, A1 B1. So that'll be 0, that'll be 0, but these two will not be 0. Does everybody sort of see that? A1 times A1 prime is going to be 0. Similarly, A1 prime times this is going to be 0. And B1 prime times this is going to be 0. How about that? So that's what you get for C2, simplified. Cool, right? Similarly, we can write and that must be equal to, using De Morgan's theorem, and now A1 times A0 prime, that's all right. B0 times B1, yeah, that's all right. No simplifications here, and no simplifications there, so this all has to get written out. And that's what I got. So taking this whole circuit and reverse engineering it and simplifying it gives me some Boolean algebraic expressions. Now, does that make a multiplier? How does a multiplier work? Well, if this is 0 and that's 0, the output should be 0. If this is 3 and that's 3, then the output should be 9. In other words, 0 times 0 is 0. Anything times 0 is 0. Anything times 1 is itself. In other words, it works like regular multiplication. But then the question becomes, is this doing that? Do these expressions represent the truth table for these 4 functions? And how would you know? How would you know? Well, you could do what I did. Write it out. 0 times 0 is 0. 0 times 1 is 0. 0 times 2 is 0. 0 times 3 is 0. 1 times 0 is 0. 1 times 1 is 1. 1 times 2 is 2. 1 times 3 is 3. 2 times 0 is 0. 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6. 3 times 0 is 0. 3 times 1 is 3. 3 times 2 is 6. 3 times 3 is 9. Here are the 2 bits representing 3. Right? That's the A part, and that's the B part. And they get multiplied together to give us an output. So that's 3 times 3. And here's the actual number. 3 times 3 is 9 in decimal. I'll just put it out. Radix equals 10. And these are row numbers down and through here. So now let's take a look. It says here, this one, C3, is true when A1, A0, B1, and B0 are all true. So here is C3 over here. We go down and we say, yes, it's true when everything's true. So C3 is correct. Let's look at C0. C0 says it's true when A0 and B0 are both equal to 1. So let's have a looky-loo. A0 is 1, B0 is 1. Sure enough, C0 is 1. It's 1. Here it's 1. Here it's 1. That works out great. So, looks like that's correct. Now we've got this much more complicated looking thing here. This is going to be true when we see the pattern. Let's rearrange this a little bit. C2 equals A1, A0 prime, B1, or A1, B1, B0 prime. I put it in this order so that I could have an opportunity to examine for the pattern 1, 0, and that should be B1. So one thing I could do is I could put it in a canonical form. That's not a bad way to go, actually. So it would be A1, A0 prime, B1 times B0 or B0 prime. That's a form of 1. And I could say or A1, A0 or A0 prime times B1, B0 prime. So if I do it that way, then what I end up with is C2 equals A1, A0 prime, B1, B0, or A1, A0 prime, B1, B0 prime, or A1, A0, B1, B0 prime, or A1, A0 prime, B1, B0 prime. From this longhand notation, I can get the indices. 0, sorry, that's 1, 0, 1, 1, which is equivalent to 13. I got 1, 1, 1, 0, which is equivalent to 14. I got 1, 0, 1, 0, which is equivalent to 10. I got 1, 0, 1, 0, yeah, which is also 10. So I got 13 and 14. Let's see, 10, 13, 14, looks like, unless I've made a mistake. Let's just make sure. So that's A1, A0. Guess we got that in two places. A1, A0 prime, B1, B0 prime. A1, A0 prime, B1, B0 prime. Yeah, it is in two places. It is in two places. That's all right. So 13 and 14 looks like they're going to be asserted as true for row for C2. So let's look at C2 and look at 13. Looks like I got that one wrong. 10 is right. I got 11. I don't see 14. Yeah, 14's there. So I got 14. It says 13 should be a 1, but why would that be true? Let's see. 3 times 1 is 3. Doesn't quite work. That doesn't quite work. So I've made a mistake in there somewhere. It's not quite sure where. But now you've got an idea as to how to do the reverse engineering from a complicated circuit into the Boolean algebra. I've made a mistake in my simplification somewheres, I'm pretty sure. Don't know where. And then after you do your simplifications, you can get yourself a canonical form. And with the canonical form, you can proceed to, yeah, these two numbers are the same. I'm just 1, 0. I'm just looking at it again, just for yucks. I figured maybe I've misinterpreted one of these things. But in any case, this is the way in which you would go about doing the forward synthesis. The reverse engineering is required because the forward synthesis will get you an optimal form using minimal sum of products. But if you're presented with a circuit, and this one's badly drawn, that's why I printed this one here. If you're presented with a circuit, you should be able to reverse engineer the circuit, figure out what the canonical sum of products looks like, and see if it matches the specification for how multiplication should work. So if you can work out the specification for multiplication, and then you can reverse engineer the circuit, you should be able to get back to the original spec and say, yes, indeed, that circuit implements this spec. It's a rather harder way to do it, in my view, because you have to reverse engineer the circuit. And that's what we're doing when we're extracting the Boolean algebraic symbols that the circuit represents. So it's a true-false question. Number 14, is the following a 2x2 binary multiplier? And the answer is yes, it is. And it's a deceptively difficult question. Deceptively difficult. So that's question 14. The answer is true. So I don't know if you have any questions about that, but what I did and over here was I did the multiply, then I figured out where each one of these columns is going to have a 1, and then I proceeded to, yeah, that should say sigma m of 1, 5. I proceeded to do the canonical sum of products in shorthand notation. And having done that, I had a full specification for my multiplier. With that spec, I could have used four variable K-maps, gotten a minimal sum of products, but that minimal sum of products form would not have had the same structure as what we see here. So this is actually a rather different implementation because it's multi-level logic. Any questions about 14? Sorry for the blemish where things didn't work out exactly right, but we got close. Now, we got our homework 7 and it's due on Monday. Are there any questions about homework 7? No questions? Number 11, you got it. I'm going to get a fresh sheet of paper because I've made a mess. Number 11. Let me see what I can do with that. Okay, so number 11, what we've got here is a classic piece of, we'll call it solid state technology. We have a piece of silicon which has been doped with something that has an excess of electrons and something which has a deficiency of electrons. And they call the one with the deficiency of electrons p-type material, and they say it has holes in it, but what they really mean is they have a valency or an outer shell which is deficient by one electron, and they add a material which is deficient by an electron, and they call that a p-doped material. Then there's something called the electron doped material, or what's known as the n-type material, and it's put right next to the p-type material. And what you get in here is electron migration, combining with the holes. And when the electron combines with the hole, it falls to a lower energy level, and it emits a photon. And this is called electroluminescence. If you were to take a black body radiator, which would consist of a piece of carbon, block of carbon like this, drill a hole in the carbon, and then heat it to a temperature of 5,000 degrees Kelvin, it would glow white hot, and that would be a daylight calibrated light source. Here you can get a similar sort of effect, only without having to go to 5,000 degrees Kelvin. This radiates. If you were to take a high temperature piece of metal, like tungsten, and raise it to a very high temperature, it won't melt because tungsten has the highest melting temperature of any metal we know. Pump out the air so it doesn't oxidize, and then presumably it'll glow white hot and it'll look like daylight. And the 5,000 degree Kelvin bulb looks like a daylight bulb, even though it's not really 5,000 degrees Kelvin. Similarly, they call that incandescence because it gets so hot it incandesces. You can take a tube with a phosphor and run electrons bouncing off the phosphor emitting photons, and they call that fluorescence. And so you can illuminate by incandescence, fluorescence, or electroluminescence. So the LED is illuminating by electroluminescence. And this is going to have a voltage drop of about 0.7 of a volt. And that's typical for a silicon-based semiconductor like this. And what does that mean to me, the electrical engineer? Well, I know that my power is equal to current times voltage, and these things could run on like 3 volts. And now I have to have a voltage drop of 0.7, so that has to be dissipated. If the current that runs through this is 1 amp, then 1 times 0.7 is going to be equal to 7/10 of a watt. And that's how much power I have to dissipate from this LED, or else it will destroy itself. The heat will destroy it. And so there's an inherent inefficiency in the LED, and still it is far more efficient than the incandescent bulb. And that is question 11. So if you look at page 669, you'll actually see a description of all of this. And one of the things you'll notice is that these light-emitting diodes have long leads and short leads. And the long leads are the positive side, and the short leads are the negative side. And if you hook it up backwards, it doesn't work, and could even damage it. And if you go to page 669 in the book, you can see the anode and the cathode, the positive, the long side, and the short side. And the electricity only flows in one direction. And then, if you read the book, you can see right over and through here, there's a 7/10 of a volt drop. And so you can actually see that's being documented for you. And this is cool too, you can make resistor diode logic. And in fact, you can have what the diode transistor logic, or DTL, is needed because the transistors amplify since the diodes drop voltage. So after the diode has dropped the voltage, you go into a transistor and you pump the voltage back up again. And that was the principle behind all the diode transistor logic which existed so many years ago. Nobody uses it anymore, but that's the old style logic. Yes? It's 0.7. Yeah, 0.7. So then there's this this reading assignment. Okay, what I'd like you to do, there's a little section here called Carry Look Ahead Circuits. You can skip that. All right, so that's like page 251. And you want to skip it. Let's see where we can go here with this. There, now it's on the screen. And then that goes all the way up to the multipliers. Which is on page 266. So skip the carry look ahead adder, go right to the multipliers on page 266, and then read the rest of chapter 5. And that'll keep you in good stead, because it'll show you how to do the partial product accumulation for multipliers, and it'll show you how the half adders and the full adders are structured to create larger multipliers. And eventually that'll take you to the end of the chapter, page 275. So you'll be reading 266 to 275. And you'll be reading everything up to page 251. So for chapter 5, that means 240 to 251. So read 240 to 251, read 266 to 275, skip 251 to 266. That's the carry look ahead adder subject. We're not going to cover that in any detail. It's interesting. I mean, there's nothing wrong with it. It's just not particularly educational right now. It'll let us proceed through the material just a little bit faster. And it's not on the homework or the test, so why bother with it? Any questions about the reading? Okay. Any questions about homework 7? Anything you want me to cover? Number 16. Whoa. Excuse me. So number 16 says 0, 1, 0, 0, 1, base 2. And you have a 5-bit binary number here, 1, 2, 3, 4, 5. And we're supposed to get the 2's complement for the 5-bit binary number. So I'll form the 1's complement and add 1. Excuse me a minute. And then 1, 0, 1, 1, 0 plus 1. Oh, jeez. And then that gives you 1, 1, 1, 0, 1. And so that's base 2. So that's a correct answer, I think. That's what I would have gotten. What do you think? Any questions about that? So when someone says, write the 2's complement of a 5-bit binary number, first thing you want to do is put in the leading 0, count the number of bits, 1, 2, 3, 4, 5. Form the 1's complement, add 1. Here's the 1's complement. That means you invert all the 1's. You're adding the 1. And then you add the 1, and that's your answer in 2's complement. Any questions about that? Any? Sure. So someone said, write the 2's complement for the 5-bit binary number. So they give you the 5-bit binary number. You count it. Make sure there's 5 bits. 1, 2, 3, 4, 5. Then it says 2's complement. So to form the 2's complement, you form the 1's complement, which means you form the negation, the bitwise negation of all of the bits. Then you add 1. And so here's the bitwise negation. 0 becomes 1. 1 becomes 0. And then add 1. There it is. And now you add 1 plus 0. You get 1. And 1 plus 0, 1 plus 0, 0 plus 0, 1 plus 0. And now that's the answer. Now you could... Yes? One plus 0 is equal to 1. Are you suggesting 1 plus 0 is equal to 1 and carry the 1? Third row. So here's the original. 0, 1, 0, 0, 1. Okay, that's the original. Now I form the complement. 1, 0, 1, 1, 0. So far so good, right? That's the complement. I took the bits and I inverted them. Now I'm going to add 1. Right? 1 plus 0 is equal to 1. There's no carry. Right here. 1 plus 0 is 1. Yes. Yes, that's exactly right. So that's how I got this. Base 2. And then and that's the answer. That was question 16. Oh, sure. So what are the steps that we take in order to form the 2's complement of a negative binary number? And the answer is we complement and then we increment. So complement and increment. Well, increment means add 1. Yeah, when I say x equals x plus 1, it is adding 1, but we could also say we have incremented x. So complement, and in fact the machine instruction from the PDP-8 computer from Digital Equipment Corporation was CIA for complement and increment the accumulator. And that's how they did what they called TAD, or 2's addition. Let's see. What is the 2's complement binary representation of the decimal number minus 13? So if I were to formulate the number 13, that's the number 13, with a leading 0 to make it positive, I would then complement this number and get 1, 0, 0, 1, 0. Then I would increment, and I get 1, 0, 0, 1. And so that's my answer, and it matches the correct answer in the homework. Base 2. Is that good? Sure. So that's minus 13 in binary using 2's complement. I think it's time for a fresh piece of paper. Let's see if we can find one. I've been blowing through my graph paper here. And the phone is ringing off the hook. You know, nobody ever calls me except when I'm in class. I'm like, hey, it's class. And I give people my schedule and everything, but they still have to call. Okay. Let's see. What other questions do you have for me? 21? You got it. 21. Okay. So, that's a half adder according to the book. And the half adder has a truth table. It has a carry out, and it has a sum out. 0 plus 0 is 0. 0 plus 1, 1, no carry. 1, no carry. 1 plus 1 is equal to 0 carry 1. So S0 is equal to A0, B0, exclusive OR. Carry out is equal to A0, B0. And what you see here is carry out equals A0, B0. And then somebody says, the sum is equal to A exclusive OR B. I'll write it nicely now. There. Made it nice. So that's how you get that. And this is the half adder. And that can be the first stage in a multi-bit adder. So the first stage in a multi-bit adder is pretty simple because it has no carry in from a prior stage. But it does have a carry out, which means if you want another bit, you're going to have an accommodation for a carry in, which means you're going to need a full adder. Now the full adder is just a little bit different, right? Because it's got a carry in. And now if we look at it that way, things got a little bit more complicated. Here's the carry in. And here's the sum out, and here's the carry out, and these are both 0. And now you can see this is a rather more complicated truth table. And if you want to number the truth table, you could proceed to do 2 3-variable K-maps and get a minimum sum of products for your full adder. But now you can chain a bunch of full adders together and add lots and lots of bits together. You could have 16 or 32 bits worth of full adder if you like. So it's clear. This is the full adder. It's rather more complicated than the half adder, because the full adder has to have an extra variable on input. Any other questions about homework 7? No questions? Well, which number? 29. Let's go all the way to 29. 29. Oh boy, it's a big one. Okay, I think we need a fresh piece of paper for that. Let's see what we can do. It says here, what is the 12-bit 2's complement of the decimal number 123? Oh, I can see where this is going. Let's see. So I'm going to find the top of the paper relative to this camera so I don't have you off screen. Okay. So he's asking for the 12-bit 2's complement of 123 base 10. So I want to know what is minus 123 using a 12-bit number in base 10. What's my first step? Well, that's a good one. Let's do that. Let's turn it into a binary number with repeated division. So 2, 1, 2, 3. I think that's a very fine idea. 61 with, well, perhaps 1 left over. And then we have 30 with 1 left over. Then we have 15 with 0 left over. We have 7 with 1 left over. Then we have 3 with 1 left over. Then we have 1 with 1 left over. Then we have 0 with 1 left over. Did I make any mistakes? Professor Lyon knows how to divide by 2. Yay, okay. So that must be equal to 1, 1, 1, 1, 0, 1, 1, base 2. Now somebody said something like 12-bit. What does that mean to me, the implementer of this negative operation? Well, I have to count bits. 1, 2, 3, 4, 5, 6, 7. I only got 7 bits here. So what do I do? Yeah, let's put in the zeros. So 1, do I have enough room? Let's do it over here. 1, 0, 1, 1, 1, 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So leading zeros don't really change anything, but they give me some space. Base 2. And someone says I have to complement and increment the accumulator. So what that means to me is this gets inverted. And then I increment. I guess I did that right. Let's take a look. And the other thing I can do if I want to express it as a literal is I can put in 0b in the front, and that will tell the compiler that this is in binary. And now I need to have 5 ones. 1, 2, 3, 4, 5. Looks like I did make a mistake somewhere. How many bits in this thing? 1, 2, 3. Let's just make sure I got this right. Did I have too many bits? Over in here? 1, 2, 3, 4. 1, 2, 3, 4. Oh no, I forgot the one over in here. I didn't copy it right. Oh no. Bummer. All right, do it again. It's okay. Do it again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm just going to get my little colored pen over in here and group them by 4. Just so I can keep it straight in my head. And now, complement. That kind of looks like an answer. 1, 2, 3, 4, 5 ones. Yep. Let's group it by 4s again. Yep, that's correct. Yay. Yeah, that is literal expressed to the compiler to let it know that what comes after is in binary format. So what you can do when you write these things out in hexadecimal, you can say 0x FEED, and the compiler equals integer x. So this will set x equal to the decimal corresponding value of the hexadecimal FEED. And if you wanted to, you could do the similar thing with 0b, where 0b is the literal that expresses to the compiler that what you have typed is in binary. And the compiler will convert that into a decimal quantity internally. Well, internally it's all binary, but when you print the variable, it'll come out in base 10, unless you tell it otherwise. Any other questions about 29? How about other questions for homework 7? No questions? I can do new material? Sure. So if I have 1 plus 1 plus 1, where the carry in is 1 and the 2 bits are 1, I have 1 plus 1 is 1, 0, plus 1 is 1, 1. So it's 1, carry 1. So this is the carry in. So when you have carry in and 2 1s, the output has to be a 1 for carry out and a summation of 1. Why? Because 1, 2, 3. There's 3 coming in, and so the binary for 3 bits coming in as 1 is 1, 1, which represents the sum of 3 bits. And then if you wanted to, you could, in principle, do a K-map. And then the summation variable, s, would be equal to 1, 2, 4, and 7. And now it looks like it's going to be all exclusive OR. So that's A1 exclusive OR, B exclusive OR, C. And then similarly, you could do the K-map for the carry, and it's going to be 3, 5, 6, 7, and then you can loop here, and loop there, and that'll be AB or BC or that one, which would be AC. And that's carry in, and that's carry out. So you can see this is rather more complicated than what we had up in here. It's still using the exclusive OR, but the carry out got a lot worse. And the exclusive OR is a little bit more complicated because it's got 3 input exclusive OR. What do you think of that? You weren't able to combine anything here, you see. Nothing combined. But I can go ahead. Go ahead. Sure. Yeah, well, actually, KMAP will give you a minimal form for the full adder, but what it doesn't do is it can't be simplified any. Um, maybe you could implement it with. Well, you could implement it with a multiplexer. Could probably do it with a 4-to-1 multiplexer. Right? You could group it 2 at a time. Right? And then you could say, well, here comes my carry. And then 0, 1, 2, 3, 2, 3. And then 0, 0. 1 is equal to C in. 2 is equal to C in. And 3 is equal to 1. That's a good way to do it, right? If you got a 4-to-1 multiplexer, that'll give you a carry out. And then for your summing junction, well, I guess you could do it with the 4-to-1 multiplexer, or you could just say I've got a fancy exclusive OR gate. There. That's actually easier because you assume you have a 3-input exclusive OR gate. Okay, I know they don't have 3-input exclusive OR gates hanging around in the shop. So if you wanted, you could implement it with the 4-to-1 multiplexer. I just got lazy. What do you think of that? Any other questions about homework number 7? No questions? Really? Number 10, you got it. Now, let me explain to you about the reading. You see, it's really important to read the book. Because you see, here's the answer right there. It's an exclusive OR gate. And so that question comes straight out of the book. So if you guys are reading the book, you can see it. And also, this is the hardware structure for an adder subtractor, right? Because this is a full adder, right? In fact, that's a full adder, full adder, full adder, full adder. And now, what do we have? A not add subtract line going in. Not add means if this is a 0, then what it's going to do is it's going to select B0, B1, B2, B3, and it will add a carry input of 0, which means it's going to work like a regular old adder. But if you assert this line as a 1, it will be in subtraction mode, which means it's going to select B0 prime, B1 prime, B2 prime, B3 prime, which is complementing the input to the accumulator. And if you put the 1 in on carry input, it's going to increment the accumulator. In other words, this is doing complement and complement, right, and increment. And as a result, it gives you a way to leverage the existing full adder hardware in order to be able to do subtraction. So it's a twofer. You get to add and subtract all with the same full adders. All you need to do is find a way to complement the variables and provide for a carry in. And all you need to do that is to assert the subtract line. But at the end of the day, if there's going to be an overflow, then this is going to light up right in through here with an exclusive OR. And so if you look through the selections, exclusive OR is one of the selections. So it's right out of the book. This is chapter 5, part of your assigned reading. This is page 250. You can see it's figure 5.8. So you guys should be reading. It's important. It's, how do I say it? An obligation to the course. Also, you can see over in here, the 3 variable input is implemented for the exclusive OR that we talked about, is implemented with two input exclusive ORs, and that gives you 3. So that's a nice way to get a 3 input exclusive OR. And then here's the carry out, and this is there's the expression for it right down in there for the carry out as a function of carry in A and B. And then here is an implementation for it. So my implementation's probably no better than theirs. It's all the same. So I am on page 250 of the book. And we do use this book, so you kind of have to read it. And that's good, right? Because you've got a lecture that's consistent with the book. And by the way, I spoke to Professor Cavello about trying to be consistent with the numbering scheme for the K-maps, and so he's going to try and do that in the future if you come across any more K-map issues. I think you had mentioned that to me, so I did discuss it with him. We'll try and be consistent with the book and with the lecture, so as not to confuse. Any other questions about homework 7? How about the multiplies? You guys got the multiplication stuff down? Absolutely. So let's try, instead of a random example, let's do a homework example. Shall I try and do the 8 by 8 multiply for problem number 5? Would that be good? Or do you already know how to do that? Okay, let's try that. So what is the output for an 8 by 8 multiplier if the input is 1, 1, 0, 1, 0, 0, 1, 0? Is that 8? 1, 2, 3, 4, 5, 6, 7, 8. Yep, that's 8. And then, next one is 1, 0, 0. 2, 3, 0, 0. And we want to multiply. Okay. Multiplication consists of AND operations. The multiply table. Yeah, let's do the multiply table. I don't know, it sounds a little boring, but in binary it is kind of actually. Okay. So here, let's learn our multiplication tables in binary. 0 times 0 is 0. 0 times 1 is 0. 0 times 1 is 0. 1 times 1 is 1. There, now you've memorized the multiplication tables. It's AND. That's what it is. It's an AND. Right? 0, 0, 0, 1, 1, 0, 1, 1. What's the output? 0, 0, 0, 1. Right? This is A, this is B. Here's AB. Right? It's AND. So all you have to do is have an AND operation. 0 times everything is 0. 0 times everything is 0. 1 times everything is itself. Running out of room here. I'm scratching this out just so it gets out of the way. Here comes a train. Look out. Ah! Oh, darn, I missed another train. You know, I've never taken that train. One plus one is 1, 0 plus 1 is 1, carry the 1. 1 plus 1 plus 1 is 1, carry the 1. 1, carry the 1. 1, carry the 1. Here comes the 1. 1, 1. Okay. And you can put in a leading 0 if you like. But let's just take a look at what we got. It's, how many ones is this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 ones. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 ones and 3 zeros. So that's correct. So I did it. I did it. How's that for an example? That's a bigger example than you probably wanted. But that's actually from question 5 in homework 7. So what happens is you're getting a shift, right? Every time you do the AND operation, and then you have to do partial product additions. And when you start to read about multiplication in the book, you'll see exactly how the hardware is structured in order to make that work. So that's actually quite interesting, because there's hardware that corresponds directly to these multiply circuits. Let me bring one up for you. Right. So here's the network of multiplies, and so here's bitwise multiplications being thrown in with carries and sums, and so that's an interesting way to go about doing these things. So you have an AND operation coming in. A full adder for the partial product addition, and those things are effectively allowing you to sum this side with, well, multiply this side with that side. And so it's a hardware matrix, right? And that gives you your 8 by 8. Now, in modern, well, I don't know if this is modern, but in medium scale integrated circuit transistor logic, the 74285 gives you 4-bit quantities for multiplication, and you can use them together in order to get an 8-bit multiplier. So this is a way to build a multiplier using transistor logic. So there you go. It's a few different opportunities for you to explore interesting implementations of multipliers. But this is the basic idea, right? This is kind of like the way we learned how to multiply in elementary school, with a difference. And the difference is it's just ones and zeros. But in some ways, the rules of multiplication are the same. 0 times anything is 0. 1 times anything is itself because you have the identity. And then the addition is all in binary. That's the tricky bit. And then the other tricky bit is keeping everything lined up. Here, I think the graph paper really saved me because it got me neat. And when you work these problems, I think neatness counts. Did you want to see another multiply? All right, so let's do one more. Let's see if I can find one here in the homework. Okay, here's question 13. Is multiplication on the computer being done with repeated addition? In other words, I don't know what this number is, but if you had to add this number to itself that many times, you'd be sitting there a real long time with the computer. A real long time. So are we using repeated addition when we multiply? And the answer is no. So 13 is false. We do not use repeated addition. So that's a, sort of a basic. Could you? Yes, you could. Has it ever been done? I don't know. Maybe yes. But that's not how modern computers work. Let's see if there's another multiply. I'm searching this now for multiplication questions. I thought there was another one. Maybe not. I'm just going to do a quick search. Multiply. Yeah, I guess not. Unless you guys can see another multiply. Which number? That was it? Okay. All right. Well, look, it's about 12:49. Let's see. We got about perhaps 2 minutes to go, and I don't think I want to start anything new. So why don't we end the class just a little bit early. It's 3:13 instead of 3:15. Unless you guys have some questions about homework 7 for me. That's due on Monday. You've got your reading assignment. Nice and warm out and sunny. Enjoy the day. Stay safe. And thank you for your attentions. Thank you. Thank you.